Good afternoon, everybody. Welcome to the last day of DEF CON 26. Yeah. And I'm assuming most of you are still waking up. But this will be a really good presentation. Wang is going to be, or Wang is going to be talking about attacking the macOS kernel graphics driver. So please give him a hand and welcome him here.
Yeah, hello everyone. Welcome to my presentation, especially during lunchtime. My name is Wang from DD Research America. What I'd like to share with you today is related to macOS graphics driver vulnerability and macOS kernel security. I started to pay attention to macOS kernel security last year, including kernel driver development, bug hunting, and vulnerability exploitation. Before that, I preferred to study the Windows kernel security and Android Linux kernel root. After entering the macOS kernel world last year, I learned a lot of well-known kernel vulnerabilities, and I picked up 4 of them as a background for today. The first case is from Ian Beale, from Google Project Zero. And the CVE number is the CVE 2015-3712. It's a NVIDIA GeForce driver arbitrary kernel memory write vulnerability. This vulnerability can eventually lead to code execution due to lack of input parameter validation. And at here, you can find a POC. The second vulnerability comes from Cisco Talos research team, which is a non-point dereference bug. It seems that the non-point dereference type of vulnerability can be exploited 2 years ago, which also means that I'm late. You can see that there's a full exploit code on the exploit database, which is a good starting point for exploitation research. And the next case is from my friend Chen Liang. The attack surface he chose is user mode graphics daemon. And he won the Pontoon game with this vulnerability 2 years ago. The user mode daemon associated with the graphics library has certain permissions, and they are usually accessible in the sandbox process. And the logic of those daemons is usually very complicated. This condition determines that the daemons are nature attack surface. And you can get more detailed information from the write-ups. The last is also from KingLab. The CVE number is 2016-1815. It's an I/O accelerator family out-of-bounds kernel memory write vulnerability. The graphics rendering engine is one of the hardest hit areas on any operating system platform, from the Win32K driver on Windows to the I/O accelerator family kernel extension on macOS. The type of those 4 vulnerabilities I choose ranged from non-point dereference, double free, and use after free to arbitrary kernel memory write vulnerability, and also ranged from user mode to kernel mode. This case has repeatedly reminded us that the graphics security cannot be ignored. So therefore, I decided to start my macOS kernel research from here. And part two is from end-day POC to 0 days. When I decided to investigate the Apple graphic driver vulnerability. Last year, I started my research from the POC samples from EMBio, such as the 2017-2443 and the 2017-2489. The reason for choosing this example is that they are very easy to learn. The logic of the POC code is clear, and the amount of the code is less than 100. We can take the first one, the 2443 as an example. 2443 is a kernel arbitrary code execution vulnerability. As you can see, the target of the POC is Intel FB client control. It's number one in green color, and the input selector here is number 3 in blue color. The input selector is 291 in hex format, and then the only thing we need to do is fill the input buffer with random garbage data. It's number 3 in red color. So just this. So I think for the security research community, each of us will think about how to start a new round of kernel code auditing from here. After I had this idea, one of my friends told me that starting from here might be a waste of time because the binary has already carefully examined by Google Project Zero. This reminds me of my Windows kernel font scalar engine vulnerability presentation at Black Hat USA 4 years ago. At that time, Jura from Google Project Zero found a large number of kernel font scalar vulnerabilities. But I can still find new kernel double fetch 0 days in the code that has been audited, such as CVE 2015 1819. So this time, I still want to give it a try. But then I began to feel that my friend was probably right. My fuzzing tool didn't have any validated output on the first day. And even the breakpoints I set it in macOS kernel didn't trigger. Fortunately for me, I didn't give up at that time. Otherwise, I don't think we will meet today. When I analyzed the root cause, I found at least 3 problems hidden the work of my fuzzing system. Without first serving these problems, the whole system will become very efficient. There are 3 obstacles. The first one is target selection, and second one is a filter driver protection, and third one is unremarkable selectors. Let me discuss it in detail. First one, target selection. There are many different targets on the macOS system, from kernel extension to internal classes. And we mentioned before, Intel FB client control is just one of the very small branch of the graphics kernel. I list some of the target drivers here. There are a lot of from AMD to NVIDIA to Intel, and also IO family drivers. It's a AMD Intel is like a mini pod driver, and the family driver is a more general driver, kernel driver. And I think as a professional security researcher, we should not miss any possibility. And next one is more important. The second obstacle is the filter driver. Before touching the target graphics driver, there are usually filter driver that protect them, which can cause our fuzzing tool to fall into an effective loop. in this figure, we can see that before touching the graphics driver, Apple, Intel, frame buffer, ASO, filter driver, Apple graphics device control is defining against the malicious input for the graphics driver. Here is the filter driver in red line, and the green line is a graphics driver itself. More specifically, in this example, selector 707 represents FB set EDID, and correspondingly, in the filter driver here, if the input buffer length is not equal to 408 bytes, all fuzzing attempts for the interface are meaningless. This means that if we only rely on the static analysis of the target driver and then build the fuzzing process, it's obviously not enough. We need to consider the entire architecture of the graphics driver set. Otherwise, we are just wasting our time. The third obstacle is unremarkable selectors. After actually getting to the target driver, I found that there are still some hidden control codes or selectors. And I found there are also the control code affect the efficiency of the fuzzing system indeed. These control codes are important because they are the key to open the door to another world, meaning that there are a lot of unknown code behind their stores. After extracted all the validated control codes with IDE script last year, I found at least one such key. It's 800000 and some random data. As you can see, after entering the corresponding handler, there's another word hidden there. And after taking their three small steps, things quickly become clear. And I found a lot of problems in just one day. Let me share some examples with you. The first one is unpatched log panic caused by a division by zero error. But be aware that the root cause behind this error is out of bounds read access to the input buffer. It's a division by zero. Register R12 is 0. And case 2. Case 2 is an unpatched local panic caused by non-point dereference. And the root cause of the problem is that the driver incorrectly initialized and dereferenced the variable. At here, RSI register is 0, and offset is 3F70. The next case is a kernel stack-based buffer overflow vulnerability. As you can see here, this stack overflow vulnerability is mitigated by stack cookie. So, in order to exploit this case, we need to have the kernel arbitrary memory reading capability. Fortunately, I quickly found one. CVE 2017-13383. Combined with the two vulnerabilities, we can bypass the stack cookie protection and gain kernel arbitrary code execution capability. But compared to kernel arbitrary kernel memory reading, I think kernel arbitrary memory writing capability is often what we really want. And here is an example. CVE ID 7155. And through it, I find more cases. such as CV 2017-7163. Yeah, let's take let's take this one as an example to discuss the kernel arbitrary memory write vulnerability. The root cause of this vulnerability is that frame buffer driver lacks input validation and sanitization. As you can see here, this instruction, it's a little small. This instruction, move EDX to RAX plus RSI. This instruction is going to write value in EDX to the offset of RAX plus RSI. And RAX at here is a base address of a kernel object. We can locate it through the arbitrary kernel memory read vulnerability. And we can control the ESI register at here. It's RAAA. We can control this register. This means that we can control the target memory address of arbitrary write primitive. And then we can fully control the EDX register at here. EDX is all controlled by attacker. This means that we can control the value to be written. The above conditions are perfect to achieve arbitrary memory write arbitrary values. So in my opinion, the quality of this vulnerability is pretty good. Yeah, but I still choose to report it to Apple last year. Because I'm not using my laptop, I'm unable to make the demonstration. I didn't take the video for it, but trust me, this type of demo is boring. Just run the exploit and pop up root shell, and the quality of this because the quality of this vulnerability is pretty good. So it's very easy to write exploit code for this. I think you can give it a try. Yeah, the first part is yes here. From NDPOC to 0 day. The next part I think is more interesting. A Kimon framework and other projects I did last year. Last year, one of my tasks was to build a kernel monitoring system for our DLP project, data leakage prevention project. And when I went to study the existing kernel monitoring interface, I found that the building monitoring mechanisms were not very friendly for third-party development. Specifically, there are two building monitoring mechanisms available: kernel authorization subsystem and mandatory access control policy subsystem. But the bad news is that they are not suitable for the current security-related kernel development tasks. The kernel authorization subsystem was introduced in the macOS 10.4 Tiger kernel in 2005. And the problem now is that this callback interface lacks the necessary maintenance and have not been upgraded for about 13 years. For the scope file operation. Number 2, for the file operation listener, there are only 7 file operation related callbacks available. I think which is obviously not enough. There are only file open, close, delete, read write, rename, exchange, and create process. But I think it's obviously not enough. And for the file operation listeners, they are unable to block any file operations. Just notification. Just notification is unacceptable. Say we detect a ransomware, and we can only watch it. and we cannot block it. So if my endpoint security solution is this, I think my boss might fire me. And for some specific callbacks, the input parameter often lack critical context information. For example, for create process callback handler, the input parameter is missing command line information. This is very important to us. And in the file operation callback handler, we cannot distinguish between new file creation and open existing. It's also important to us. And for we know the listeners, not every file system operation triggers an authorization request. This means that our monitor can be bypassed. It's also not acceptable. Compared with kernel authorization subsystem, mandatory access control framework has a series of more granular callback interface, which are introduced into kernel from macOS 10.5. 10.5. However, Apple quickly banned third parties from using this interface and claimed that this interface were not part of the KPI. KPI is short for kernel programming interface. This means that mandatory access control framework is totally private. We cannot use that interface. But if you really want to use that interface in kernel, since we are all kernel extension, we have permission to locate the target function in kernel and then invoke it. If you really want to use the interface in kernel, I think you will meet the following compatibility issues. I reviewed almost all the kernel open source code about Mac policy. And I found this one, the following cases. The case one shows that the interface were deleted or replaced directly by kernel. This is unacceptable because the feature disappeared directly. I cannot accept this. And case two shows that protocols and the input parameters were changed directly. It's also unacceptable because my driver will panic. You cannot add a parameter directly into the prototype, right? And case 3 shows that the interface was inserted into the middle of the dispatch table. Yeah, my driver will panic too. And here's the case 4. The interface has been rewritten but forgot to upgrade the policy version number. So my point is that as a third-party developer, we have to use this mechanism very, very carefully. And in order to bring out some changes, I'd like to introduce you to Kimon, open source pre- and post callback-based framework for macOS kernel monitoring. Since there's no patch guard or similar kernel self-protection subsystem, I built the pre- and post operation callback interface based on my kernel inline hook engine. By using this framework, I can add new features to any function I care about. The idea of the pre- and post operation callback architecture is actually borrowed from Windows kernel. Generally speaking, in the pre-callback handler, I can filter the input parameters. And in the post-callback handler, I can reset the function's return value if needed. I have 2 examples here. The first one is a kernel extension monitor or a kernel extension firewall. I know there are similar functions in mandatory access control policy mechanism, but I still want to use my own method to achieve it again. As can be seen here, the first line is a callback handler. And in the pre-callback handler, I can filter input parameters. It's small. Such as I can get the UID, I can get PID, parent ID, and the kernel extension name is com.magnet.monitor, and the path, and also version number, module base, and module size. In this case, I use a file magnet tool. It's named monitor.app as an example. The reason is just because it contains a driver and will load that driver into kernel. This is true. In the post callback handler, in the pre callback handler here, I'm using a disassembler to search the endpoint of the target driver, and I can patch the driver endpoint. So, as can be seen here, the driver failed to load. And in the post callback handler, I can reset the function return value if needed. Another more interesting example in the mandatory access control policy is a mandatory access control policy monitor. So are you wondered about which module in the system use the mandatory access control policy, and which policy set do they use? I think here is the answer. As can be seen, the first one I dumped from kernel is AMFI. AMFI is short for Apple Mobile File Integrity, and it's all handlers of this module, including base address, a module offset, and policy name. As can be seen, AMFI and this one is Sandbox. Mac Sandbox registered a large number of Mac policies. The tricky part of this feature is how to get the mutex lock. I mean, we need to hold the lock before accessing kernel data structures. But the policy mutex lock is not exported. But fortunately, I finally found a way to lock that mutex lock, and you can review my code for more information. And in addition to enumerating and monitoring mandatory access control policy, Kmon can also block or handshake arbitrary handlers if needed. In this case, I still use the file magnet tool monitor.app as an example. The reason is this tool will try to register 5 MAC callbacks. The first one is for process monitoring. The second one is for dynamic library monitoring. The third one is for keyboard monitoring, and it's file operation. Last one is kernel extension. And Kmon can block those requests. Here's an example. Demo. I demonstrated this at Black Hat Arsenal 3 days ago, and I didn't make the video for it. But don't worry. Talk is cheap. Show me the code, right? Definitely. I released all my source code. Please check out my source code for more detailed information. In addition to the 2 applications above, I also implement a kernel fuzzing helper by using Kmon framework. I call it Keeper. Keeper can randomly inject errors, assist in recording the input parameters, and call stacks of the graphics driver. For me, this feature are very helpful. As can be seen here, I inline hooked the Intel FB client control do attributes, and this is my fuzzing tool. A selector is a random, and the input data is it's also random. This figure shows that the input data is random data, and I can do bit flipping here. Actually, I also implement another tool, also project for monitoring IPC communication. Okay. Yeah, the last part is discussion of 0 days and macOS kernel protection. First, let me show you a graphics driver related to 0 day. I have a simple demo. This system has all the system patches installed, and after running my POC, the system crashed. This is reboot. And here is the call stack information. It's a heap overwrite vulnerability, and the panic call stack shows that it's a victim thread. This victim thread is accessing the corrupted heap, and this is another crash thread. In fact, they are all victims of the vulnerability because the thread crops the heap is not theirs. And the root cause of this vulnerability is the following piece of code. Let me give you some background on this code. The input, in the yellow color, the input is the length of my input tent data. And the length of the input data should be a multiple of 10. All numbers are in hex format. It should be a multiple of 10. And the general logic of this code is that it processed one round every 10 bytes. If the final length is less than 10 at here, if the final length is less than 10, the code breaks the loop. So, can you find the bug in this code? I find the bug manually. Yeah, the problem comes from this subtraction operation. If the input buffer length is greater than 10, this code is fine. But if the buffer size passed in is less than 10, you can see here less than 10, this subtraction will cause an integer overflow. And then a memory copy here will destroy the adjacent heap. And I submitted this vulnerability to Apple Security this week, and I also met them this morning. I'm sure the vulnerability will be fixed soon. And to protect against the threat from the graphics drivers, I did some extra work based on the Kernel framework. By using the kernel inline hook engine, I hooked up some key functions of graphics driver, such as do attributes interface. As can be seen in those handlers, I can filter the opening and the setting operations of untrusted domain. The untrusted domain is my graphics further process. So which means I can reject some malicious requests. By the way, I'm very much hope that Apple can add the similar functionality to kernel through the mandatory access control policy and or dtrace interface. Yeah. Yeah, it's almost my presentation. We discussed the bug hunting, zero-day vulnerabilities, and the KMon open source project. And I also mentioned third-party kernel protection and mitigation. I released all the source code. Please check it for more detailed information. Yeah, that's it. Thank you, guys.